All right. Let's see here. Should be live for any of y'all out there. Apologies for the technical difficulties, but hopefully you're seeing a screen and you're seeing me. My name is Lawrence. You're seeing me on camera. I think we should be good to get started. Again, apologies for the late start. I promise we'll make it up with the content that we'll be talking through. But okay, so welcome to our Hoot. My name is Lawrence, like I said, from Solo. I'm a field engineer here at Solo, and today we're going to be talking about eBPF, a top-down view. And so the goal for today is to kind of get a high-level overview of what eBPF is, as well as kind of a hands-on approach to actually building and running some eBPF programs. So let me go ahead and get this slideshow going. Should be able to see the slides. Okay, so eBPF, a top-down view. So like I mentioned, we're going to kind of get into an overview, kind of the fundamentals of what eBPF is. Then the top-down view portion will actually dig into what really is happening and why this technology is so powerful, and then we'll see a hands-on demo. So to get started, eBPF. What is it? It stands for Extended Berkeley Packet Filter, which is, it actually is kind of an evolution of the original BPF, which stands for Berkeley Packet Filter. The reason it's called that is, as the name sounds, it was originally for filtering packets. And so if you think of TCP dump, or several other of the tooling in the Linux world or Unix world for filtering packets, that is how BBPF is how you do that. And so with TCP dump, for example, if you've ever used that in order to capture network flows and so on, what you're really doing is you're telling TCP dump to basically say, I want to capture packets that are TCP or UDP, and they're from this source address to this destination address and so on. And the way that worked is by using the Berkeley Packet Filter subsystem. And so eBPF is an extension of that, where now, rather than only working for packet filtering, it essentially is a way to handle any type of custom logic that you want to essentially embed into the Linux kernel without having to change that. And so here on this second bullet point, this is really more, I actually saw some of the maintainers for eBPF have talked about, the technology has kind of outgrown the acronym. It's a technology, not an acronym. And really what it is it's a technology that enables you to embed custom logic and attach it to various points in the kernel and elsewhere even. For example, one of the things that you can do with eBPF is you can actually attach to user space applications. But I would say the majority of the most common use case, at least for now, is for attaching to various places in the kernel. It's also event-based, so I call out think JavaScript. So basically, as an event happens in some type of kernel functionality, you can then do something in your eBPF code. And one of the other really important things about this extended eBPF that's really important is that the programs that you write are verified to be safe, which means that now you can you have a guarantee, or at least you have a close to a guarantee that the code that you're writing, the programs that you're running won't crash the kernel. They're guaranteed to return. You can only access specific sections of memory and so on. So it gives you a lot of confidence to run, kernel. You're essentially writing kernel code, but it gives you some safety that you're not going to essentially crash your kernel. And this is one of the really important benefits of eBPF compared to things like kernel modules, where if you load a kernel module and it's faulty, you could crash the kernel and, in other words, bring down the entire system. So there's a lot of value here that eBPF has provided, and recently it's become a very popular technology for valid reason, because it essentially gives you kind of endless flexibility of being able to modify and run custom logic in the kernel without having to actually make changes in the kernel. And we'll get into some of the more specific things that you can do with it here in the rest of this talk. So, what is an eBPF program? So, eBPF, like I said, the technology has kind of outgrown the acronym. There's a lot of components to it, but at the most core level, what you're doing is when you write an eBPF program is you're writing some code that will, again, run in the kernel. And so, I call out this quote here. This is from kind of the unofficial BPF documentation. There's a link here. I can send this out. But basically, an eBPF program is simply a sequence of 64-bit instructions. And so when you ultimately what you're doing is you're writing some code, and we'll get into what that code looks like. But ultimately, it gets compiled or what have you into a set of 64-bit instructions. And eBPF runs as a VM in the kernel, which with its own instruction set. You can also think of it as bytecode. And so you have essentially what looks like assembly, right, that are specific to eBPF. And when you basically will write code in higher level language, compile it to this assembly, and then that assembly contains that's the actual instructions for what happens for your program. And in most cases, on a lot of the most common architectures, you actually can that bytecode will actually be JIT compiled to essentially run natively. So if you're writing some eBPF code and you compile it to your assembly, then on common architectures that will get JIT compiled into native code, native machine code. You're essentially running as pretty much as fast as you can go. So now you have this custom logic that somehow is running as fast as it possibly can on your system, and that's really important for the types of things that you want to do with eBPF. Whether that's tracing or whether that's network policies and so on. You're getting the flexibility of being able to load this in kind of outside of like making changes to the kernel, but it also will run at a native speed. Here on the bottom, this example is a little it's kind of in the weeds, but the main point here is that given some eBPF program that's been compiled into assembly, we can actually look at the assembly, and this is what this looks like. So you can see that there's registers, there's function calls, and so on. And so it's not too different from any other assembly that you may be familiar with, but again, this is specific for the eBPF VM running inside of the kernel. So kind of taking all that and thinking about what's like a standard workflow, you'll write some eBPF program code, and here we're calling out in C. What you'll see as we go through this is you typically, kind of the most common way of writing eBPF code today is you write in a C-like language. And I call it C-like. It's referenced as C-like because the syntax is C, as you may know, but you don't really use things like libc, like you don't have the standard library and so on. You can only use specific eBPF helper functions and built-ins and things like that. So you're not writing like system C, but you're writing using the C language. You're writing your eBPF program. Then you'll compile it, probably using Clang. I actually don't know if there's another compiler that works today for compiling to eBPF assembly, but you write your code in C, you use Clang to compile it to eBPF assembly or bytecode, and that's stored as an ELF file. We kind of briefly looked at that in the last slide. That was the end result, was that eBPF code or program was compiled into an ELF file that contained your eBPF assembly. Then you'll take that ELF file and the various programs that are in that file, you load them into the kernel, and you also create the necessary maps. We'll go into more detail of what maps are, what eBPF maps are here in a second. And this process is typically done for you by a component that's typically called a loader, which makes sense because you're loading programs into the kernel. But you can also do it through system calls, and we'll take a look at some of those here in a second. Then once the code is loaded into the kernel, the programs are loaded into the kernel, then you actually attach them to whatever hook point you need to. So we'll get into more details, but this is basically loading the program into the kernel is not enough, right? You have to load it into the kernel, and then you actually have to attach that program to do something, and you do that by attaching it to the hook points. And that, as we mentioned, think event-based, right? So the hook points are essentially more or less saying, okay, based on this hook point, I'm going to receive an event for, say, when I receive a packet, right? And then you can do whatever you want with that data. And then that's kind of the last step, right? You read and analyze that data. So those maps that we talked about come into play here, but ultimately, your program will do something, right? And more than likely, it's going to be operating in some sort of data. So then you need to read and analyze that data. And that's kind of the high-level workflow of an eBPF program. So getting a little bit more into the details of loading and attaching. So like I mentioned, the loader usually takes care of loading your program into the kernel. But under the covers, what that's really doing is it's using this BPF syscall. And you make this syscall with your program, and you get back a file descriptor. Kind of similar to, pretty much everything, like the common saying is everything in Linux is a file, or more accurately, a file descriptor. What happens is you load your program into the kernel with that syscall, and you get back a file descriptor that references the program that you just loaded. And so that's what you'll use to kind of do all of the rest of the plumbing for whatever it is that you need to do with that program. So the hook points that we talked about depend on the type of program that you're writing. So some of the this is a very small list of examples, but things like trace points, kprobes, socket filters, XDP, which stands for Express Data Path. There are lots of types of BPF programs that you can write, and based on that type, that is how you can then that determines where you can attach them to. And through the rest of this example, we'll be using kprobes a lot, so I'll go into more details there. But it's important to call out that based on this type of program that you're writing and where you're attaching it to, you actually will use different tools and different system calls to be able to attach your programs to those hook points. And so I mentioned kprobes is what we'll be using. Kprobes, I'll come back to this. To call out what a kprobe is, and if you're not familiar, this is straight from the kernel documentation. Kprobes enable you to dynamically break into any kernel routine and collect debugging and performance information non-disruptively. What's important about that is that basically any kernel function, you can use a kprobe to basically get a copy of all of the memory or data being accessed by that kernel function. And that's really powerful because pretty much anything anything fundamentally that happens in your system, you can theoretically get access to it with a kprobe. And we'll go more into detail of like what they look like, but you just know that kprobe gives you access to basically the access to the data being passed into any kernel function. And so in order to attach that for kprobe specifically, one of the ways you can do that is by using this perf event open syscall, and then followed by ioctl syscall. And what you're really doing there is, since kprobes predate eBPF, and they are part of like the perf subsystem. And so really what you need to do is you need to tell that system that, hey, I want to attach a kprobe to this function, more or less, right? And so with eBPF, what you're doing is you're attaching, first you're telling the kernel that you want a kprobe on a given function, and then you are using ioctl to attach your eBPF program to that kprobe. So we talked about eBPF maps. This is kind of these kind of are your fundamental, this is how you really get data to and from your BPF programs. And this is important because especially since we're talking about things like observability and tracing and so on, you need to be able to access that data to make sense of it, right? And so the eBPF maps are a way to do that. I call it here, they're data structures used to store data gathered from the program, share with other programs, etc. There are lots of types of maps, and these represent different types of data structures. You can also get into things where like you can have maps that are created on certain CPUs and so on. And they can be accessed by the BBPF program as well as the user space program. And that's important because, you know, if you want to do something with that data, you need a way to access it from user space. And these maps are the way to do that. Similar to the other components that we've been looking at, it's also created with that BBPF syscall. So in other words, you can create it from user space, right? So you can make a syscall to create it. Again, this is also something that's typically done for you through your loader. And we'll get into more of that later. So to kind of give you a more visual representation of what is actually happening when you build in the eBPF program, this is kind of the, I'm not sure if yeah. So this is a very small snippet of what a program would look like, right? And we'll get more into the code later on, but just know that, you know, you have some, you're writing some eBPF code, and then you compile it using Clang, and you're calling out that the target's BBPF, and the output file is, in this case, this TCP connect.o file. And then when we run that command, if we look at what that file actually is, you'll see that it's an ELF file. And I, just to make sure, ELF is and actually, let me make sure that you can see that last. Yeah, okay. So ELF is the standard kind of executable format on Linux. And so you're getting what looks like a standard executable format file, even though it's really just a way of representing some compiled eBPF code, right? And so as you can see, this is, we have an ELF file that contains the code that we just compiled. And then what you want to do is, if we kind of look in that file, what we can see is, here we go. I think, yeah, okay, so it's kind of lagging a little bit, I apologize. But if we actually look inside that file, you'll see that, and this is a standard ELF format, you basically have sections that represent different pieces of data, more or less. And in this file, we have all of the various things like the license. We talked about maps, and then in our example, in the previous example, we have various kprobes and kret probe, which is essentially, so the kprobe is when you enter your kernel function. The kret probe is right as you return from that function. And so you can see that we have the kprobe and the kret probe for TCP v4 connect, which is what we wrote our probes for. And so when we compiled that program, we got an ELF file that has assembly more or less for each one of these programs. And then what we'll do is we will take that and load that program into the kernel. And that's how we get our eBPF program, and more specifically the actual type of program into the kernel. So for example, if we focus in on this TCP v4 connect kprobe, right, what we're really going to do is, as we parse through this file, or more accurately, as the loader parses through this file, it will look for sections that have, for example, kprobe / TCP v4 connect. It will know that, okay, I need to attach this as a kprobe, and the content of this kprobe, or the actual code that represents this kprobe, is in this section in the ELF file. So what our loader will do, and again, you could do this by hand, but there's no real reason why you would want to do that unless, I guess, you were trying to test something out. But what you do is you take that probe and that section and that bytecode or assembly that represents that program. You'll make a call to the BBPF syscall, and you'll tell it, I want to do a program load, and then you pass the program details. And so in this case, what the program details look like is it's a BBPF prog type kprobe. So you're saying that I know that this is a kprobe because of the section name, for example, and here is the bytecode, which is in the ELF file at this section. So what you do is you need to load that into the kernel. And that's what the syscall accomplishes. The last step is that your program is essentially validated by what's called the verifier. And the verifier is the component that makes sure that your all of the things that we talked about at the beginning that make up the safety of the program. So things like, that it returns and, it's not an endless loop. It only accesses memory in the correct space that it's supposed to, and things like that. And the verifier is what actually performs that verification. And if your program doesn't pass the verifier, this call will fail and the program is not loaded into the kernel. And that's how you get that safety of not, of making sure that your program will not blow up the kernel or do something nefarious, something like that. It's worth calling out that the verifier can be, a bit finicky. So even if you're writing code that you think is accurate, the verifier may reject it, and that just might be because you are not initializing memory in a way that it expects, or you're not doing something with pointers in a completely correct way, or you're inferring. So the verifier is probably something that will give you trouble, but that's where it helps to kind of dig into what commonly is done. The verifier will tell you exactly where it's rejecting your code, but it does this in a pretty low level way. Essentially, it tells you, what in the assembly, for example, which register is not passing the verification. And then you can take that and kind of work backwards and figure out where you need to make your code more explicit or where you need to change something. But once that is done, now you get back that file descriptor that more or less points to your loaded eBPF program in the kernel. So to take a quick break from kind of the actual specifics of getting the programs into the kernel and so on, to actually write this stuff, it's important to kind of know how you can do that. And so one of the things that, so these are kind of some of the options that you have. The top one is like one of it's probably not a realistic option, but since the eBPF program is ultimately just represented as assembly or bytecode, you could in theory write that by hand. There are actually some really interesting use cases that do exactly this. But it's not something that you probably don't want to do that unless you have a really good reason to, or if you're just interested in learning the assembly. There's actually a really cool, I probably should add a link to it. There's a user space implementation of the eBPF VM. So if you wanted to, you could write some assembly by hand and run it through the user space VM to make sure that it would work. But again, that's not really something that it's not really for realistic. Or at least the standard use case. The next one is BCC. This is kind of one of the original frameworks, if you want to call it that, for writing BBPF programs. I have the description straight from the README here. But basically what you do with BCC is it's very tightly coupled with the system so you write some code that's in the BCC style, and what you do is you more or less write it. You ultimately get, it says here you can do Python or Lua. I'll use the Python example. You basically have a Python script that contains BBPF code as C that is treated more or less as a string in Python. And then when you actually run your Python script, BCC will take that string that has your code, do the compilation with it basically has Clang and LLVM as part of it, and it will do the compilation on the fly when you run it. And so it actually, it's a pretty solid tool, but there are downsides to it because of exactly what I just said. You have to compile it on the fly, and you ship around Clang and LLVM as part of the binary, more or less. And so it works, but it also has some basically some cons as far as like portability and so on. Another important thing is that when you're writing code for BCC, you typically are writing your BBPF code to use the kernel structures directly from the Linux headers, more or less. And so what that means is that you're writing your code for a specific version of the kernel, and you are depending on the headers to be present. So that's kind of two downsides right there, because the headers are not present typically that's more of a dev environment type thing. running that in production is your production servers typically will not have the kernel headers present. And then on top of that, the kernel, the actual kernel structs change pretty much every version. And so if every kernel version. And so if you're writing it for one version, the way that the fields are structured or the way that they're ordered and so on may not be the same on other versions of the kernel. And so there's some downsides there as far as portability goes. And that's actually what the next one, eBPF is trying to solve, which more or less is the kind of production style, more modern way of writing eBPF programs. And so this is kind of an example here where eBPF program code is normally written in the C language with some code organization conventions added to let eBPF make sense of eBPF code structure and properly hand everything into the kernel. This is taken from eBPF Bootstrap, which is a getting started guide more or less for eBPF. And this blog here that I link out is a really great resource for everything, pretty much eBPF. This is, I believe, I don't know how to say it. I don't want to butcher it, but Andrei Nakriko. He is one of the core maintainers. I think he's also kind of like the tech lead of the eBPF structure. And so what this really does is this attempts to solve the portability challenge with two components called BTF and CORE, or compile once, run everywhere. BTF stands for BPF type format, and this is we don't have time to get into the details here, but really what it's intending to do is allow you to compile your eBPF code into a binary that you can then ship around, and with the BPF type format and CORE, that means that as long as the kernel supports BPF type format, you can run your code on any version of the kernel that supports that type format. And it allows you to do things like, you're not depending directly on the kernel structures. This library more or less knows how to handle different versions of the kernel headers or of the structs, and will automatically kind of relocate based on which version you're running on. And so kind of, again, to condense it, eBPF is the kind of future forward, more production style way of writing eBPF programs. Then just quickly, I'll also call out, there are high level tools like eBPF Trace, which is an interesting tool that kind of essentially is trying to give you a higher level language. You can think of something like awk is very similar, that allows you to write eBPF code without getting into the very, the weeds of writing like C and talking to kernel structures. So that's another option as far as like kind of higher level tooling. So that's, we'll move on from this. There's another tool that I'm going to touch on at the end that we as Solo we wrote, that will help. The goal is to make it even easier for getting started with eBPF, and we'll touch on that here in a second. Quickly, to get into the top-down view, this is kind of like, so we've kind of talked about what the technology is and what it does, but how it actually works is something that I think is a little confusing, and when you see what we're actually doing, it makes a lot of sense. In my opinion, it helps kind of make everything click. So if we want to do something like trace a network connection, in this case we're using curl, and we're just making a curl to 1.1.1.1, and that's just a server that lives somewhere over the internet. So if we want to actually trace this, what we could do is we could have some type of instrumentation in curl that will keep track of connections and so on to a given server or a given destination. But let's see how. So what we'll do is we'll kind of go down into the Linux stack to understand what's actually happening and how we can use eBPF to help with that. So kind of at the top level, ultimately under the, when you make this curl request to connect to 1.1.1.1, curl itself has to actually establish that connection. And the way that it does it is with, in the curl, there's a lib for connect.c. And what that really ends up doing is calling the syscall connect, which more or less is going to just take an open socket and then give it an address that you want to connect to. And so from kind of the user space and kind of from, the application level, that's it. It says, okay, I need to make a syscall. I need to call connect. I want to establish a connection to this server. But then what happens is it starts going into the Linux stack, the network stack. And so the actual syscall makes a request here to do, on the socket, I want to call this connect function more or less for this socket. And in this case, we're talking 1.1.1.1, that's a TCP connection with curl, and we want to do this, this is IPv4, right? So there's a specific function in the kernel for making a TCP connection over IPv4. So this is not directly on the path, but down in the weeds there is a struct that basically points when you make a connect call. What that really does is it calls this function TCP_v4_connect. And so when your socket connect option is being called, what actually is happening is it's calling this TCP v4 connect function, and this is what actually performs the the real connection. So when you make this connect call, it goes to the syscall. The syscall under the cover is going to call this TCP v4 connect, and that's kind of the lowest level. That is what is actually making the connection. So if we want to trace network connections, and if we want to not have to instrument the application itself, what we can do is write a BBPF program that will use this. Basically, we're going to, in our example, we'll use a kprobe to take the, basically get an event, more or less, when this function is called, and then do something with it. So in our case, we just want to log it, or we just want to see that there is a connection being established. And so going back to our earlier example, if we have the kprobes and a krep probe on this specific kernel function, when we attach that to our on our system to the right function calls, when I as a user make a curl 1.1.1.1 without any changes at the application level, we will automatically get an event, and then whatever we're doing with the event down here, that will automatically be called, more or less. And so what we can do is, we'll go look at an example. Let's log it, right? So we'll be able to know, for example, which PID is making a request to what server. And so the power comes from the fact that we're able to do this transparently to the application. The attachment and the loading and all that is happening outside of the application process. And since, as we touched on, it basically gets compiled down to native code or native machine code, we don't have, or there's very little performance impact. And so it's a really powerful thing. And then this is just, one very kind of not contrived example, but it's a very simple example. And it hopefully illustrates kind of some of the power that eBPF provides. So we're kind of running a little bit late. I'm going to keep going. But what we'll do is, at Solo, we just released an open source project called Bumblebee, which is essentially a way to get started with eBPF that hopefully makes the developer experience, the getting started experience, extremely simple. And so we'll jump into a quick demo with this. I encourage you to go check out the website, the Git repo, the GitHub repo if you're interested. So here's our GitHub repo, go check it out. The goal really, again, is to be very straightforward, and it also provides some pretty cool things that we'll see. But really, you don't have to do much. Basically, all of the user space stuff that I was talking about is kind of abstracted away for you. You can also get metrics automatically, Prometheus-style metrics. But let's get into a demo, make some of it concrete. So I have, let me make this a little bit bigger. I have the command line tool, B, downloaded already, you can get it just by running our install script. You could also do, here's the install script. You could also, use Go if you want to. But essentially, I have that downloaded here on my system. And so if I were to do B, so I have it here. And then what we'll do is I want to write some code to do exactly what we just talked about. I want to see network connections. And so I have a single file here, this probe.c. If we look at it, we'll go into some of the details here. It's very much adapted from our tutorial. So if you are at the repo, if you're interested, this is too big. In our docs folder, there's links on the README, but we have a getting started guide that kind of talks through pretty much everything that I'm gonna show. So go check it out, go try it out. But to get into the code, what we wanna do is we want to log the PID and the IP address of every connect call, every TCP connect. And so to do that, this file is, let's see, 47 lines of code. And what we will do is we're going to create a map. Remember, the map is how you pass data to and from, either the kernel or wherever you're at. And so from the kernel to user space or vice versa if you wanted. In our case, we're going to make a map that will just simply print out whatever data we get from our event. And so in our case, again, we want to log the IP address and the PID for the destination of a connect call. And so we're going to create this map that's called events, and it is a map of type ring buffer. And the value is this event struct, which is defined up here. And this event struct contains two pieces of data, an IP address, which represents the destination address, and the PID, which is the process ID of the process making this connection, right? And so our map, which is called events, is going to receive events that contain the destination address and the PID of those, of the connect calls. And then just also call out the section. If you remember when we were looking at the ELF file for the eBPF code, this dot maps represents that it's an eBPF map that we want to load into the kernel, and we'll be using this to pass data to and from. This dot print is a bumblebee kind of specific convention, and this will tell our loader to automatically print out any event in this map. And this will make more sense when we actually run it. But this is basically a convention that says, anything that's in this map, I want you to, in this example, print it out to the screen automatically. So we're not writing any code to display it or anything. That's handled for us. And then the actual probe itself is pretty straightforward. Since we're adding a TCP or K probe to the TCP v4 connect, these following arguments are more or less the arguments that the actual function the kernel function gets. So in this case, it's a socket and a socket address. And that is, what is actually the kernel is actually using to establish the connection. So we have access to that in our K probe. And so what we'll do here is we'll initialize the event that's going to contain the data, the destination address and the PID. And then we're also initializing some memory to hold the destination address. We do a BBPF core read, which is a libbpf kind of specific helper. This is again handling the portability aspect, where this allows us to write code that will run on multiple kernel versions more or less. But really what we're doing is we're getting data from the arguments that were passed in to that tell us what the destination address is. So ultimately, this dadder variable after this call will have the correct value on whatever kernel version you're on for the destination address, IP address. Then we need to reserve some space in that ring buffer. And then we simply need to write the data. So to our event, we're writing the destination address and we're writing the PID. The PID we're getting from, this is another helper function. Again, I mentioned earlier, you can't use kind of standard, since this is running the kernel, you don't have access to like the libc, right? So most of the kind of data that you get through helper functions. This is an example of one of those helper functions, which will give you the PID essentially. The name is a little different because when you're in the kernel space, the PID is not kind of the PID that you would expect from the user space, but essentially this function gives us what we want, which is the user style PID. And so we have the destination address, we have the PID in our event. Let's go ahead and submit that to the ring buffer. So I know that was a little quick. Again, the tutorial that I mentioned on the GitHub kind of goes into the weeds and will show you, we'll walk you through in more specifics what is actually happening. So then what we want to do, we have this code. Again, that was all the code we need to write. We need to actually build it. So what we're going to do is we're going to build using the B command, the B CLI. And what we can do is we can do a B build, and we want to build the probe.c file. And then what we can do is, one of the other kind of cool features of Bumblebee is that, so in the slides we were looking at, the actual output from a standard eBPF build process is that ELF file. But what we did is we actually made it to where we have an OCI image spec that allows you to kind of package up the eBPF program in an OCI image that you can then ship around or store using any of the kind of standard, cloud native style OCI image workflows. And so what we'll do is we'll build this program that we just wrote. We're going to build that into an OCI image, and we'll call that my_probe. And since it's an image, we'll tag it with v1. So b build the file that we want to build, and then the OCI image that we're going to package it as. And so we compiled it, and as you can see, it says, we wrote it to this probe.o, and you can actually see that file does exist, right? So what we actually could even do is do this file on it, and you'll see that it is an ELF that contains eBPF. And then it's also saved to our OCI image, my_probe v1. So that is an image, right? That could be pushed to a container registry. That could be pushed to wherever you want it. It's also stored locally on my system. So what we can do is we can run it now with b run and then the name of the image. So my probe v1, right? And so the runner, this is the runner. This is the actual tool that we built that, again, since with Bumblebee, we didn't write any user space code. But it does know that there is a map called events that we want to print events for, right? And we also know the format of that based off of the code, based off of how we define that struct. So if we open up another pane and we make some network requests, for example, to that 1.1.1.1 that we were looking at, right? As we make that request, and actually here you go, I got another one just from standard system, whatever's happening on the system. There was a request from PID 459 to this 108 address, and then my curl call down here was this PID, which was the curl command that I just ran, made a request to the destination address of 1.1.1. And again, this is formatted as an IP address. This kind of happened all dynamically. We didn't have to write any code to do that. So if we send some more traffic, right, we can send more 1.1. We can go to somewhere else like google.com, right? And so this is one of the IPs for google.com. I'm sure we can run this a few times. We'll get different ones. Yeah, so 138.101. But all of this is happening without having to write any code to handle kind of the reading of the map. But then it also is, we're getting network tracing, network observability without having anything in curl to do so. And so there's a lot of power there. Again, Bumblebee is intended to make it simple to get started. What I wrote, again, is based off of the Getting Started guide. You should be able to get started as well. But this is just kind of like a, the very, very intro level to kind of the power that eBPF has, and some of the tooling that is being built around it to make it easy to get started. And then we haven't even touched on things that you can do things like I mentioned in the talk, in the slides. There's different places to attach programs to that allow you to do things like network policy, or if you want to handle a packet at the earliest possible point. If it's from, say a bad actor, you can drop it immediately before it even goes through the stack. So there's a lot of options, there's a lot of power. But with that, and we kind of ran over because we got started late, so I'm gonna stop there. I hope it was illuminating or interesting. If there are any questions, please let us know. But yeah, that's all I have. Thanks for watching, and let's see, doesn't look like there's any questions. Nope. Okay. All right, well, thank you everybody. See you next time.